All right. In today's lesson, we are going to look at rates of change. Ladies and gentlemen, today's lesson, we are looking at rates of change, specifically looking at velocity. So at some point in your math/science career, I hope that you have seen this equation, that velocity is the distance or displacement divided by time. Do we remember seeing this? Okay. So what happens is we are going to use displacement and time as our X and Y axes. We are going to plot a graph that shows displacement over time. We use the slope in order to determine what is the velocity, right? Because displacement is the change in distance or the change in position, and we have the change in time. So this is like saying S2 minus S1 over T2 minus T1. Okay, so average velocity is the slope m of the graph that is displacement and time. So in our example, they've given us a graph of displacement versus time, and it says find the average velocity between T1 and T5 seconds. Now the gap here is quite large, so we're just going to go ahead and zoom in. Where is T1? Right here. So at 1, our displacement is 30, and at 5, our displacement is 25. 20? Let's be more specific. That looked, yeah, 22.5. Just under 25. Okay, so average velocity then. Average velocity is the distance between the points. So 22.5 minus 30 divided by the difference in time, 5 minus 1. So this gives me negative 7.5 over 4. And you can chuck that into a calculator and it'll give you about negative 1.88 meters per second. What does the negative signify? Yes, I have gone back. I have moved backward. So I am closer to my initial position than I was at the start of the time. Okay, so average velocity is the same thing as the slope of a displacement and time graph. And hopefully you can kind of see this is also representative of a secant line, right? We draw a line between the 2 points, rise over run, and the goal is hopefully you can kind of predict what we're going to do. We're going to bring this point closer and closer and closer. And as we get close to the point of interest, what are we going to find? The instantaneous velocity. Yes. So that's kind of where we're going. We start with a secant line, 2 points, and as we get closer, so as we find the limit, that will give us instantaneous velocity. If we don't find the limit, then we're looking at average velocity between the 2 times. So let's look at the second example. The position of a particle is given by the function s of t equals blah, where t is a positive number. Find the average velocity, so this is your slope, between the points of 1 second and 4 seconds. So first, let's figure out what is the distance or displacement at 1, what is the displacement at 4. I'm hoping you guys will grab your calculators here. Hint, hint, nudge, nudge. 8 for which one? S1 is 8, okay. S of 4, 5. Okay, so my initial coordinates are 1, 8, final coordinates are 4, 5. So my average velocity, or I can always say V with a bar over it. Average velocity is going to be, oh, I was going to start with an 8. Nope. Final displacement minus initial. Final time minus initial. So I get -1 meters per second. So I'm moving back towards my initial position. Remember doing this once upon a time? You've probably done it in a bunch of physics classes too, right? All right, let's flip our page. So if we want to find instantaneous velocity, so the velocity at a single point in time, we need to find the slope of the tangent at that point on the graph. So here's my one sentence for the week. We are dealing with a single point in time. So that means there is no interval. Means there is no delta t or delta s because we are approaching the limit. So the solution is we can estimate the instantaneous velocity using the idea of the averages and letting the difference between our intervals get smaller and smaller. In other words, we are going to find the instantaneous velocity by finding the limit of our graph. And this is the same limit equation that we used in our last lesson. All right, with that in mind, let's take a look at example 3. Suppose that a ball is dropped from the observation deck of the CN Tower, 450 meters above the ground. How fast is the ball falling after 3 seconds? So initial velocity here is 0, right? Because somebody is holding their arm out and letting go. So initially when the time starts, we know displacement is 0, velocity is 0, time is 0. And from physics, we know that the equation for velocity is using this function. If you kind of think back, this is the d equals 4.9 t, or sorry, let me write it in a way that you would recognize from physics. D equals 1/2 at squared plus v naught t, right? But we know v naught is 0, no initial velocity, so this goes away. A is represented by gravity divided by 2. This is what we're left with. You could assume that it is negative, yes, or you could say, let's make the direction down positive. Either way is fine as long as you specify. So at the end of my result here, how fast is the ball moving, or how fast is the ball falling after 3 seconds? I'm going to get a positive number, but I'm going to say it's moving at this speed downward, right? So my concluding statement will adjust the sign as we go because it's a word problem. Okay, here's my